Having looked at the product rule, we now move on to the quotient rule. Whereas the product rule is for when one function is multiplying another function, in the quotient rule we have a function divided by another function. So u is some function of x and v is also some function of x. Now, the quotient rule says this: dy by dx equals. Now I always start by filling in the denominator because it's easy to remember. The denominator is v squared. And this reminds me to start the numerator with v. And the numerator, it looks a little bit like the product rule, but not the same. v u dash minus u v dash. So that is the quotient rule. Let's take a look at it, a couple of examples. Suppose you were asked to differentiate y equals x to the power 4 over x minus 2. Well, u is x to the power 4, v equals x minus 2, u dash equals 4x cubed, v dash equals 1. And dy by dx equals a fraction. In the denominator we need v squared, so x minus 2 all squared. In the numerator, x minus 2 times u dash minus u times v dash. So we've differentiated it, but as with the product rule, we now need to spend a bit of time tidying this up so that it's a bit more useful for whatever the question might go on to ask. Now there's one common mistake that people make here. Let me highlight that first so that you don't do it. Don't expand the denominator. If you do, all that will happen is that you will end up having to refactorize it and you'll have wasted a lot of effort. All of our work for the time being goes into the numerator. So we can just write that. In the top line, we do need to expand this, we do need to simplify it. We've got 4x to the power 4 minus 8x cubed minus x to the power 4, which gives us 3x to the power 4 minus 8x cubed all over x minus 2 squared. Now the question, of course, is whether or not anything cancels. Does this fraction simplify? To judge that, you need to factorize both the numerator and the denominator. And that's why it was a bad idea if we had contemplated trying to expand that denominator there. Because now, I'm going to factorize this top line. We've got x cubed 3x minus 8 all over x minus 2 all squared. And we can see straight away that there is no common factor. There is no factor which appears both in the numerator and the denominator. If there was, then they would cancel, but there aren't. So this is as simple as it gets. If we were being asked for the turning points of this original function, we would put 0 here to say that the gradient is 0, and we would have 0 equals this fraction. The only way that a fraction can equal 0 is if the numerator equals 0. And so we would go on to say that x cubed bracket 3x minus 8 must equal 0, and we would solve that. Let's look at one slightly more complicated example. Suppose we had y equals 2x minus 1 all squared over 3x plus 2 all cubed. And again, we're being asked to differentiate this. U equals 2, let's get this right, U equals 2x minus 1 all squared, V equals 3x plus 2 all cubed. Now, perhaps pause the video here and just make sure you can differentiate those accurately before we go on. Okay, hopefully you've had a go at that now. If we differentiate this, we get 2 bracket 2x minus 1 all to the power 1. But we need to remember the chain rule. When we differentiate the contents of the bracket, that will produce another 2. And so what we have here is 4 bracket 2x minus 1. Over here, same concept, 3 open bracket 3x plus 2 all squared, but the chain rule pulls out another 3, and so we have 9 bracket 3x plus 2 all squared. We could expand that. I'm inclined not to, for the same reason as we saw previously. We might expand it later, but not at the moment. So dy by dx equals, now we need v squared on the bottom. V is 3x plus 2 all cubed. If we square a cube, we get a power 6. So that's v squared. The numerator, v times u dash, again let me get it right, u dash minus u v dash. It makes for a very long numerator, but there we go. Now, we're going to want to simplify this if we can. And this is where I'm glad that I didn't expand this, because I can immediately see that in this term here, I have a factor of 2x minus 1, as well as other things. And in this term here, I also have a factor of 2x minus 1. If I had expanded that, then that factor of 2x minus 1 would be a lot less obvious, and I would probably miss it. So let's see what we've got. The denominator is always the easiest thing to fill in first. Let's leave it there. Now, looking at the numbers, the 4 and the 9 don't have a common factor. But the 2x minus 1 is a common factor. And the 3x plus 2, it appears in both of these terms. There it's squared, there it's cubed. So 3x plus 2 all squared is a common factor. And now I need to think carefully about what I need to put inside this square bracket. I've got a 4 that I need to account for. 4 times that, but I need another bracket of 3x plus 2. So I've got that. Minus 9. The 2x minus 1, I'm short of one bracket there. So I've got a 2x minus 1, so that times that makes this squared. But this 3x plus 2 all squared, that's already been completely removed. So I'm actually finished the numerator there. Now this numerator, let's see what we've got. 2x minus 1, 3x plus 2, all squared. Open this square bracket. I've got 12x plus 8 minus 18x, and then very carefully plus 9. And all of that is over 3x plus 2 all to the power 6. We're nearly there. There's two basic steps to do now. First of all, let's tidy up the numerator a little further. I can now see that I've got negative 6x plus 17, and that is all over 3x plus 2 all to the 6. And it's now that we finally see the real advantage of never trying to expand this v squared, because the 3x plus 2 all squared in the numerator here is a common factor with part of this denominator. So what I can do, I can cancel those two brackets with two of these brackets to leave me with 3x plus 2 all to the 4 in the denominator. And in the numerator I have 2x minus 1. That's gone. And the second bracket, I'm just going to write it in a slightly more traditional manner with the positive at the front. So 17 minus 6x. And we have now differentiated, but also tidied up the result of the differentiation.